I'm tired. I want to go home. Aren't y'all tired? Yeah. Um, any particular questions? It'll be 8 multiple choice. I mean, 8 free response. There'll be those 4 questions. The multi-loop circuit will have 3 currents you'll have to know, like I did in class the other day. And then there'll be that one with the wire where you have to find the magnetic field due to the wire, direction and magnitude, and then the force on the charge, direction and magnitude. That's 2 questions. It's 5. And then, oh, the RC circuit, you have to find the time for it to have a certain voltage, charge, or current. And then you have to draw the graph for the voltage, charge, or current for that situation. Just look at the equations. And then finally, there'll be that simple refraction problem. Just 2 media interface. It's not going to be one of those stacks of media. It'll just be N1, N2, and you have to calculate the exit angle, theta 2. All right. Are there particular questions? I can revisit those free response. I've done them a couple times in class, but I can revisit them if you want. Questions? Was that a yes? You want me to revisit the free response? Okay. Let me do some different ones if that's okay. So I'm gonna, let's see, this is spring 24, number 1. We'll do number 1 and number 4, and then we'll go to some other exam. Spring 24, this is number 1. I'm not gonna ask you question A. Instead, I'll ask you question B. Question B is how long does it take for the capacitor to reach a voltage of 6 volts? So remember to just look at your equation sheet. What am I doing? Charging or discharging? This is a charging capacitor. I know that because there's the battery in the figure. The battery is what's charging the capacitor. If there's no battery, then you know it's discharging. This is a charging capacitor. I want to know its voltage. The voltage for a charging capacitor is that growth function. This V equal V naught 1 minus e to the minus t over RC. So that's going to, I'll have to calculate that. Say V equals V naught times 1 minus e to the minus t over RC. That is 6 equals 8 times 1 minus e to the minus t over RC. That's 4 times 3. That's 12. And then I can divide both sides by 8. That's 6 over 8, which is 3/4 equals 1 minus e to the minus t over 12. That's subtract 1 from both sides. That's negative 0.25 equals negative e to the minus t over 12. Those negatives go away. You take the natural log of both sides to get rid of this exponential, and the natural log of 0.25 is negative 1.4. Negative 1.4 equals negative t over 12. So t, the negatives go away, is 12 times 1.4. That's 17 seconds. All right, so that's the answer for that one. And then I could ask you to draw the voltage, charge, or current for this. Let's just say voltage. If I were to say the voltage versus time, I would say voltage versus time. I know that it's given by this function, and that is a growth function. Okay, it's either going to look like that or it's going to look like this. If it's one of those others with just the e to the minus t over RC, it'll look like the one on top. Another free response is like this one, number 4, where a proton approaches a wire with a current of 3 amps. In this figure, there's its velocity, there's its distance from the wire. I first want to know what is the direction of magnitude of the magnetic field. So A is B equals mu naught I over 2 pi r. 4 pi times pi 10 to the minus 7 times the current, which is 3 over 2 pi times r, which is 0.1 squared, or excuse me, just 0.1. The pi's cancel. The 2 cancels with that. Just leaves 2 up there, so I get 6. I get 60 times 10 to the minus 7. Excuse me. 60 times 10 to the minus 7. That's my magnetic field. And then I also need to find the direction of that magnetic field. Use your right-hand rule. Your thumb goes in the direction of the current. They go into the page on the left side and out of the page on the right side. I need to know on the left side, so that was into the page is my magnetic field. So it's 60 times 10 to the minus 7 Tesla into the page. Or you could say negative Z. Either one of those would be fine. Honestly, if you just drew the figure there, I'd probably give you credit for that too. Just show the direction somehow. And then what is the direction of the magnitude of the magnetic force on the proton? So that is F equals QVB sine theta, but theta is equal to 90. For a proton, that's 1.6 times 10 to the minus 19. V is given, that's 4 times 10 to the 5th. And then B is that 60 times 10 to the minus 7. And then when you find that, that is that force. I'll let y'all calculate that. And then to find the direction, I say V is, my index is in the direction of V. V is into the page. My thumb then is pointing up. So the force on that charge is in the upward direction. So whatever the force is in newtons in the upward direction, or you could say plus y. All right, so that's one of the free response. Another free response is the one, it would be sort of like this, except it wouldn't have this medium, and I would just be asking what is this angle here, in which case I would say 1.2 times sine of 30 equals 1.1 sine of theta, and solving that for theta. See, 1.2 sine of 30 is 0.6 divided by 1.1. I get 0.55, and the inverse sine of 0.55 is 33 degrees. So theta would be 33 degrees. Simple refraction problem, not one like with all the media, okay? I'm not going to have you draw anything. I'm just going to ask you to calculate the angle. There is no figure, though, so you'll just have to use the words, use your words to sort of, recreate the situation. But y'all can do that. Sometimes that's more difficult for students. So that's 1, 2, 3, 4, 5. Oh, and then there's the multi-loop circuit. I'll have to go to a different exam for that. So for the multi-loop circuit, it'll be one like this. There are lots of examples in those old exams. I don't remember if I did y'all's portrait or landscape. I'm pretty sure I did it. Landscape. I don't remember. Anyway, your steps are, first, you pick directions for the current. I've labeled the currents for you. What is it? Oh, sorry. This is Spring 21. This would be exam 2. Spring 21, exam 2. First, pick directions for the currents. Doesn't matter what those are. I'm just going to pick them kind of randomly. Then I write my equations, but remember you want to pick the right loops. Since there are no resistors in that bottom branch, then you use the bottom loop and the big loop. You want to include loops or have loops that include that bottom branch because there's no resistor. So let's do the big one first. I'll start here and we'll go in this direction. That would be 2 plus 4. See, I'm coming around, I come up here, so it's plus 4 because I'm going from little to big. And then I'm going against the current, so it's plus 2I1. And then that's equal to 0. So 6 plus 2I1 equals 0, so I1 equals negative 3. Then I can also do the bottom loop because that includes that branch again. The bottom loop, I'll start here again and go in this direction. That's 2 minus 6I2 plus 8 equals 0. That's 10 divided by 3, I2 equals negative 10. 10 divided by 6, 5/3. Amp. Okay, positive. So then finally I can find I3. I use my junction rule. I like to draw the arrows up close. This is I2, this is I1, and this is I3. Notice I2 is going into that junction, and I1 and I3 are going out. So I have I2 equals I1 plus I3. That's 5/3 equals -3. Remember, I have to carry my negative over into this. Whatever negatives I find, I keep until the very end, plus I3. So I3 is equal to 5/3 plus 3. That's what, 14/3 amps. Okay. So now going up here, I1 is 3 amps. It was negative. We had chosen it to the right. That means it's opposite that, to the left. I2 is 5/3 to the left. And I3 is 14/3 to the right. You don't have to do it as fractions. You can do it as decimals. Okay? Lots of mistakes that you can make in that, so please be very careful. Just watch your signs and watch how you solve those equations. They won't be difficult to solve, but there are a lot of little algebra steps you have to take. That jog your memory a bit. We've done these in class, but it'll help you because you'll see a number of multiple choice questions that will be very similar to those. All right, what else, y'all? Yeah. Okay.
14 on exam 3, 2022.
This one? Yeah. Yeah, we were starting to look at one like this in class the other day. So one way you can do it, I've done this in class, like imagine this wire on the left. I do my right hand rule. I have my thumb go into the page and then my fingers wrap around, in this case in a clockwise fashion. So if I imagine I have this big circle that goes around clockwise in this direction, at this point P, the tangent to that circle will be in this direction, along that vector E. E is not the right answer, but along that vector E. So you can do it that way. As I said also in class the other day, a nice way to look at this too is to just simply draw a radial line out from the wire to the point, and then you know that the magnetic field has to either be in that direction or in this first direction that I drew, because it has to be perpendicular to that radial line. But then I can do my right hand rule, and I think it then becomes more apparent that it's this direction. Is that more apparent? Like when you see it like that, as it's perpendicular to that radial line, it will always be perpendicular to that radial line. So then that only gives you two options. So if you imagine that with this other wire, let me do it in a different color. If you imagine that with this one, I have a radial line that goes like that. It's going to be in that direction, right? If I think about my right-hand rule, my thumb comes out of the page, and then my fingers fold around, and so it's tangent to that circle. And so now I want to know the net vector, and that vector is going to be vector D. The sum of those two vectors that are like this is the one in between. Okay, that good? I've had a bunch of questions about that particular question. I'm pretty sure there's one like 16. Can we just make sure we're up to date on 16? This one also requires you to do a couple of different right-hand rules. The first thing that you have to recognize is the direction of the force and the direction of the velocity. I have this vector right here is going in this direction, and initially at least there's a force that is pulling it to the left. Actually, what's happening here is as this particle goes up, the force is like this, and as it travels through, those two vectors are always perpendicular one another. So this is my velocity vector, and this is my force vector. They are always perpendicular. So like these would go like that around that circle. But initially, the force is to the left, and the velocity is up. And so I need to figure out what is the magnetic field. V is the index, F is my thumb. So my middle finger is into the page. So I know my magnetic field here has to be into the page. And then it's a matter of what current causes that magnetic field. Well, if the current was to the left, well, that would be out of the page. So it has to be then to the right, which would be into the page. So B is the right answer for that one. Okay. Yeah, that's a good question. So how did I get the force and the velocity? This black arrow shows the path that it takes. So initially this charge is traveling up, right? That's the direction of the path. But then I see that it's curving off to the left. And so it must have some force that's pulling it to the side. That's your centripetal force that's causing that circular pattern, that circular path. Does that answer your question? Yeah. It's a good question. I've had that question a lot. Sweet. All right. What else, y'all? I'm pretty sure you'll have one, not exactly like number 13, but one where I don't. I'm sorry, Lily. Did you have a question? Okay. But one where I give you the directions. I don't draw a figure. So make sure that you can translate from that to a figure where you can actually apply the right-hand rule. Let's just try this. Of course, make sure that we recognize it's an electron. It's traveling in the plus y direction. So that means that my velocity is in that direction in a magnetic field that's directed in the positive x direction. So B is in that direction. And so what is the direction of the force? Well, V is up, B is to the right. So I have into the page, but then of course I remember that it's an electron, so it should be out of the page. I flip that because it's an electron. So the answer then is B for that one. Really, I said the hard part there, I don't think it's hard, but just translating those words into a figure that you can then do the right-hand rule. And do draw the figure. Don't try to just do it in your head. That's not going to work out well for anybody. Well, some of you might be able to do it, but I wouldn't try it. All right? What, did I do it wrong? Let me double check.
It wouldn't be into.
V, yeah, it is into, but it's an electron.
Oh.
So I take the opposite. See, that's why I did this circle right here. And
I got one question. I could just
keep going, girl.
Can you do 17 and 19 and 20?
Yeah. Everybody has the same questions. Oh, yeah. Okay. So 17, you won't have one this complicated, I'm pretty sure. But I'm also pretty sure that this application of the right-hand rule comes up. So I again think the radial line is useful. If I draw a radial line like that, I know that the magnetic field is in that direction. Remember, it has to be perpendicular to the radial line, so it's either that direction or that direction. So if I do my right-hand rule, I see that it's in that direction. So get rid of that other arrow. And then likewise over here, it's going to be in that direction. And then here, it's going to be in that direction. So the net vector, then those three vectors will add up to give me a net vector that's up. Because the x components of these two vectors are going to cancel out, and so I'll just have three vectors that are pointing straight up. And which one? 19. Okay, so this is from a mass spectrometer. I want to know the sign of this charge. It's a mass spectrometer because the particle's traveling in a circular path. Just pick a point on the path. It doesn't really matter where. I'll pick a point right here. My velocity is tangent to that circle. and my force is perpendicular to the circle. Remember, the force is a centripetal force, so it's always towards the center of the circle. It's also always perpendicular to the velocity. So now that I have this, I just see if this is right, given this magnetic field. V is down, the force is in that direction. So that means the magnetic field should be into the page, but it's not, it's out of the page. So that tells me it's a negative particle. Or I can do it a different way. I could say V is down, the magnetic field is out of the page. I should feel a force to the left, but I actually have a force to the right, so it's a negative particle. Okay? So because the right-hand rule doesn't work out right here, I know it has to be a negative particle. Yeah, okay, on 18, you will have one like that. Yeah. Okay, all right, let's just do it right quick. It shouldn't be a surprise. So for the mass spectrometer, this is the cyclotron equation, R equal mv over qb. I can write that down, R equals mv over qb. The mass spectrometer, you can only select particles based on their mass to charge ratio. And so I solved this for m over q, the mass charge ratio, that's going to be rb over v. R is given, that's 2, B is 6, and V is 4. That's 4, 6, 2. Those are your R, B, and V. That's 2 times 6 is 12 divided by 4 is a mass to charge ratio of 3. And then you have to go on this table. These aren't obviously real particles. That's me, that's my wife, that's my son, that's my daughter. Don't recognize it yet. Anyway, this has a mass charge ratio of 1 to 3. This is 6 to 2. Oh, that is the answer. 6 to 2 is 3. So that's the right answer. It's Kaizite. This is 9 to 1. This is 1 to 6. 2 to 12 is 1 to 6. So I'm looking for the right mass to charge ratio. And in this case, it's B, Kaizite. Kate, did you have another question? All day, right? No, that's it? Okay. All right. What else we got, y'all? 2020, 12, and 16. Oh yeah, this wasn't meant to be a hard question. It was just a little bit confusing because I have this wire and we have these other problems where wires generate magnetic fields, but this one doesn't. There's no current in the wire. I'm just asking what is the direction of the magnetic field? And so really what I'm asking is the magnetic field runs from north to south pole. So that means that it's to the right. So wasn't meant to be confusing, but this question was a little bit confusing with the whole wire in there. But magnetic fields will always run from north to south pole, the magnetic field lines. But this, I mean, you won't see one like this on the exam. And then 13, you said? 16. Yeah, that's good. So this is an electric motor where you have a loop of wire with a current running through it in a magnetic field, and that will cause it to move. Just pick one of the wires. I'll pick the one on the left. I have a current that is into the page, that's I, and then I have a magnetic field that is moving, that's to the right. So I use my right-hand rule. I is in that direction, B is to the right. So the force on that side of the wire is going to be in the downward direction, that's the force. On the opposite side, the current is just going in the opposite direction. So that means that the force on that one is up. So if you think about like a steering wheel, one side's going down, the other side's going up. That is a counterclockwise motion, at least at this point. Once it flips over halfway, it starts going clockwise. But at this point, it's counterclockwise. All right, what else, y'all? Okay, and the light stuff, you'll have some of these too. Oh, let's just do one of these. So here, which of the following is true? you'll need to know how to look at a figure like this and determine which index is bigger, which velocity is bigger. In this case, I like to think of it in terms of velocity, even though this is asking about index. I draw my wave fronts. I know that here it's going in that direction. So this is my slow medium, and this is my fast medium. Because I know in order to bend this way, it has to move faster here in order to bend away from the normal. So that means that this is my big N, and this is my small n. So N2 then is less than N1. That's B. So be able to do that, determine the right, ratio, or not ratio, but the right size of the indices of refraction, and also the right velocities, which is faster or slower. Be able to do something like 21, where you just calculate the index of refraction, or you calculate the angle. That's like the free response, by the way. So if you get the free response right, there's a problem in the exam that's almost identical to the free response. So that's a twofer. You get one and you get two. You're going to have one like number 20. Remember, that's just adding up your angles. This angle is the same as the incident. This angle is 90 minus 50, or 40. 40 plus 120 is 160. That means that this must be 20, because in a triangle, the sum of all the angles is 180. And if that's 20, that means that this angle is 70 degrees. And so then the final reflected angle is 70 degrees. So it's just really a little bit of geometry, knowing your triangles and your complementary angles. But you'll have one on the exam. Hopefully that's a gimme. You'll also have one like this, that you're able to organize the radiation in wavelength, energy, or frequency. And these have gamma, infrared, radio, and visible, but you could have any of those that I told y'all which ones you needed to know in the notes. You might want to go back and revisit that. But in this case, short wavelength is high energy, and a long wavelength is low energy. So the short wavelength is high energy. That's gamma, so that gets rid of A and D. It must start with gamma. And then the low energy should be on the other end, which is radio. Radio is the lowest energy. And so that's, excuse me, the longest wavelength is radio waves. Radio waves can have wavelengths that are thousands of kilometers. It can be really long. So those are the same. We can't distinguish there. So we need to figure out infrared or visible, which has a longer wavelength. That would be the infrared. So C is the right answer. Just be able to order those by not just wavelength, but also frequency and energy. The order of frequency and energy is the same. Energy is proportional to frequency, and wavelength is inversely proportional to frequency. So for wavelength, it's switched. They're swapped. All right. What else, y'all? Yeah. The last one. Which one? This one? What number? 21? 20? Oh, this one. Yes, I went through that fast. I'm sorry. Let me erase what I have here. All right. So as I said, you will have one of these. So make sure that you don't miss it. The first thing, you just want to start here and step through with each angle. I will give you this angle and that angle. It'll look exactly like this, except this angle will be different and this angle will be different. But I know that theta I is equal to theta R, so that angle has to be 50. I also know that this angle is 90 degrees. That means that this is 90 minus 50, or equal to 40. And then I see this triangle. Ah, shoot, that's not right. That's 120, 40. 120 plus 40 is 160, and the total must be 180. That means that angle must be 20 degrees. So this angle right here is 20 degrees. I just blew up that triangle so you can see it better. Then if that's 20 degrees, this is a 90-degree angle, so this must be 90 minus 20, or 70 degrees. And then that means that this one is also 70, because theta I is equal to theta R. Okay, so two things you need to know. The 90-degree angle, those complementary angles, and then the sum in the triangle is 180. Oh, and then theta I is equal to theta R. That's that law of reflection. That okay? Good. Other questions, y'all? There is a gimme question, by the way. I think it was like, who is my favorite student? Do y'all know the answer to that question? Who? That's right, Eli. Yeah. There'll be one like this with the equations. Where's the equation? Yeah, like one of these with the equations. Which equation is right? Let's just sort of go through this, okay? So on these, I put them in order. So you just go with the first number. Like, so for example, A starts with 14. That means I'm going in this direction. So 14 minus 4I1. So far that's correct. Plus 6. Oh, but it's 6I3. It should just be plus 6, but it has I3, so that's not right. And then here, 14, again, positive, going in this direction, minus 4. Oh, it has I3. That's the wrong current. Minus 6. That would be this one, but going in this direction, minus 6, plus 10. That's right. Plus 6I2. Is that right? Plus 6I2? That is right, because I'm going against the current, so it should be positive. So the answer is C there. You will have one very similar to that. I mean, you know, different equations on a different circuit, but you do the same thing. David? Number 2? Absolutely. Yeah, on a circuit breaker, you have these devices, and when you add the blender, the circuit breaker turns off. So you will have a couple questions about home circuits. You need to know those 3 devices, the GFCI, the circuit breaker, and the grounding. And then you could also see a question like this. Just sort of you need to know how the household circuit is laid out. You'll see on all the exams there are a couple questions. On this one, you know you want to calculate the current for each one. The current is equal to P divided by V. So for example, for that first one, it's 1200 watts divided by 120 volts. So that's 10 amps. So I had 10 amps for the first one. The next one is 60 divided by 120. So that's 0.5 amps. That's just 60 watts divided by 120. I tried to make the numbers easy. The 240 watt, that's 2 amps. That's 240 divided by 120. So that's 12.5 amps. Your current or your circuit is chugging along just fine with 12.5 amps in it. But then you turn on the blender, which is 180 watts, and I add 180 divided by 120. That's 1.5. So somewhere between 12.5 and 12.5 plus 1.5, that's 13, and 14, somewhere between there, the circuit turns off. I'm working just fine at 12.5 amps, but when I try to put 14 amps, the circuit breaker turns off. And so I'm looking for a number between 12.5 and 14. Obviously, that's B, 13 is the right answer. Okay, that good? Calculate the current for each one. Find the sum of all the devices that are working just fine, and then add in that extra device, and then somewhere in between those two numbers is your answer. Sometimes it's 15, like most household circuits are 15, but it doesn't have to be. I don't think any household circuit is set for 13 amps, but you know, it's just an exercise at this point. Some of your household circuits are 20 amps, and then also like for if you have, depending on the wiring that you have, or if it's just lights or outlets, and then some of them are 30 amps or even 50 amps, or it depends on the devices that are on them. All right, what else, y'all? This one? Yeah. Okay, so this is like the other one that we did. Let's see. So I have 30 degrees right here. So what must that angle be? That would be 60. Yeah, 90 minus 30 is 60. And then a 60 plus 50 is 110. That means that 180 minus 110, that's 70 degrees. So this angle is 70 degrees, which means that this angle is 20 degrees, which means that this angle is also 20. That is the reflected angle off of the second mirror. Okay, is that good? Definitely gonna have one of those, okay? Practice those on your own, try them out. They all sort of work in the same way, more or less. What else, yeah? All right, I'll call it done then. Let me just make sure I got everybody.